Alright, this video is going to deal with the review questions from Unit 13 in the review packet, which are questions 26 through 30. Okay, make sure you have a reference sheet handy as well as your calculator, since this unit is very, very math heavy. Lots of formulas and lots of calculations. Okay, so the first question is 26, where it asks you to state the relationship between the variables and explain why it occurs. So first thing, as far as the relationship goes, you want to understand whether the reaction is, not the reaction, the variables are directly or indirectly related. Okay, so pressure and volume, if you think about what happens there, think of a balloon. If you squeeze on the sides of a balloon, you are decreasing the pressure, because the pressure is getting smaller, but those same particles of gas are now packed into a smaller space, meaning they are going to be hitting the walls a lot more, they're going to be hitting each other a lot more, which means a lot more forces, which will in turn increase the pressure. So if volume decreases and pressure increases, that means these two would have an inverse, sometimes also referred to as an indirect relationship. Alright. So again, the reason being, as the pressure increases, the gas particles are more likely to hit the as the volume decreases, the gas particles hit the wall containers more, which would in turn increase the pressure. Okay? For volume and temperature, temperature, remember, is a measure of the average kinetic energy. So if the kinetic energy increases and the temperature increases, that means that the gases are going to move around a lot more and they have a lot more room to so the volume would increase. So if the temperature is increasing and the volume is increasing, we would see that these two have a direct relationship, or in other words, they are directly proportional. Okay, they both go up or they both go down. We see that the other one involving temperature, pressure and temperature, also will have a direct relationship for the same reason. If the temperature increases, then that means there's more kinetic energy, the molecules are moving around a lot more. If they're moving around a lot more and a lot more chaotic, that means they're going to be crashing into each other a lot more. And remember, pressure is really a measure of all of those little collisions and forces. So the more forces and collisions there are, the greater the pressure. So we'll see that these also have a direct relationship, because if one goes up, so will the other one. If the other one goes down, so will the other. Okay? So you want to understand those sort of generic relationships there. The remainder of the questions, we're actually getting into the math behind them. So we want to figure out which formula can we use to solve this problem, and then actually solve it. Okay? So question 27, our general process here is always to figure out which variables we have in the problem, and then go from there. Okay? So if we look at this one, we see a volume. Now how would you know it's a volume? It says it, but also because of that unit, milliliters. So we have a volume. We also have a pressure. It's in torr, but torr is still a pressure unit. And then it asks, what would the pressure be if the gas is allowed to expand to this new volume? It says the temperature remains constant. If the temperature remains constant, it means it's not really part of the equation, so we don't need to worry about it. So we're looking for an equation that involves two volumes and two pressures. There's only one formula that has that. It is Boyle's law. P1V1 equals P2V2. I don't care if you don't really remember the names of the formulas, you just need to be able to apply them. So if we start plugging our values in then, this volume and pressure go together, because it says it has that volume when the pressure is 755. So we have to make sure they go on the same side of the equation. So I'm going to plug in 755 torr and 15.25 milliliters. And then on the other side, we don't know what the pressure is going to be, but the volume would be 0.55 liters. Now, if I just write this, we have a quick problem here. This is in milliliters, and this is in liters, which isn't going to work. So I need to change one of them. Doesn't really matter which one you change. But if you think about our conversions here, to go from milliliters to liters, we used our King Henry scale. The liter is the base unit, and we're going all the way to milli. So if we're moving that over, we're starting at liters and going 1, 2, 3 spots to the right. So we take our decimal place and move that 3 spots to the right, which means 0.55 liters becomes 550 milliliters. Now we see that the units are going to cancel, so we can solve this. Alright, so we're going to divide both sides by the coefficient of our variable, the 550 milliliters. If we do that, those will cancel. Notice what happens with the units. Milliliters cancel, we'll be left with torr. So if you do the math, 755 multiplied by 15.25 divided by 550, we'll see that our pressure at this new set of conditions comes out to about 20.9 torr. Okay, this does make sense because based on our relationship, we know that pressure and volume are inversely related. So if the volume goes up, which it does, the pressure should go down, and it went from 755 to 20.9. So it did indeed go down, proving that inverse relationship. Okay, now moving to our next one. All right, so in 28, same drill. If we look at all the numbers we have in the problem, we see a volume. That won't always say a volume, but milliliters should tell you that that's a volume. We also see Celsius, which is a temperature, and it asks to what volume, so that's a new volume, would this gas expand if its temperature became this? So we see two volumes, two temperatures. There's only one formula that has two of both of those. It is Charles' law, V1 over T1 equals V2 over T2. Okay, now the big thing you have to remember with this one is that temperatures must be in Kelvin. Remember, we talked about this a lot in this unit. Anytime you plug in a temperature into a formula, you have to make sure they're in Kelvin. Okay, now if you forget how to get to Kelvin, you take the Celsius temperature and you add 273. So if we start plugging in, our volume, the first volume, it said we had 275 milliliters, and in our formula they're divided, so we'll divide by, but rather than 25, if you add 273 to 25, that would be 298 Kelvin. One way to remember, I mentioned this to my class at least, if you're worried you're going to forget about the temperatures, then I suggest what you do, just cross out the Celsius temperature right away and fill them in right in your problem. Okay, so we'll just make that 298, and if you did the same thing with 220, if you cross that out and add 273, that would be 493 Kelvin. Then it saves you maybe a step at the end. Okay, so we have our V1 over T1, and then on our other side, we don't know what the new volume is, but we are solving for what the temperature would be at 220 degrees Celsius, which we converted to 493 Kelvin. Now the easiest way to solve this one, this is a proportion, right? So the easiest way would be to cross multiply. So if we cross multiply, our setup would now be 275 milliliters multiplied by 493 Kelvin equals 298 Kelvin multiplied by the volume. So to solve for our variable V here, divide by the coefficient of our variable. Those are going to cancel. Notice that Kelvin also cancel, leaving you with milliliters. Once again, it didn't matter which volume unit you used for this problem, just so long as they matched up. So our final answer here, V2, so I really should have put V2s here, so we just remember there. V2 will come out to about 455 milliliters. Here we see a direct relationship at work, because notice that in our proportion here, the temperature increased, and our volume then should increase as well, which it did. 455 is indeed more than 275. All right, so that's question 28. On to question 29. For question 29, same drill, let's underline and see what we have here. So we've got 28 degrees Celsius, that's a temperature. We have a volume in liters, and we see a pressure. And asks us to calculate the final temperature when its volume is this and its pressure is this. Alright, so our only formula that has two pressures, two volumes, and a temperature, the only one would be the combined gas law, P1V1 over T1 equals P2V2 over T2. Okay, so same drill as before, we just need to make sure that the 1s and 2s, their units match up, and our temperatures need to be in Kelvin. So rather than 28, let's cross that one out and recognize that that would be 301 Kelvin, and we'll cross out, and we're solving for our other temperature, so our answer will come out in Kelvin already then. Okay, so our setup would look like this then. We would do P1, oops, alright, so P1 was 1.49 ATM, our volume was 65 liters, and the original temperature was 301 Kelvin. On the other side, P2 was 1.93 ATM, the second volume was 50 liters, and we were solving for this temperature in the bottom. So once again, even though it's a little bit more complicated, you can still cross multiply to solve this one. So if we cross multiply these and these, you would get 1.49 multiplied by 65 multiplied by our variable t2 equals 301 multiplied by 1.93 multiplied by 50. Now notice the units, ATM would cancel on both sides, liters would cancel on both sides, and we're going to be left with Kelvin. So if we divide both sides by the coefficient of our variable here, you can also simplify and just make these single numbers if that's easier for you. If we do that, we'll see that T2 equals 301 times 1.93 times 50 divided by this product in the denominator. So all in all, that would give you just around 300 or 301 Kelvin. Okay? So when we have multiple variables changing, you can't necessarily say whether the relationship would be direct or indirect, just because there's too many things changing at once. So just be sufficient to check your math and make sure you didn't skip anything. Okay? For our last problem from this unit, we have a volume. Oops, excuse me. It asks us what is the volume. When you have this many moles, moles we represent with the variable N. It gives us a temperature, and it gives us a pressure. Once again, let's automatically change that 23 degrees Celsius to a Kelvin temperature. Okay, but this is the only formula the only time we've seen a problem so far that has this variable N in there. So what do we do with that? There was only one formula. So our one formula that has the N in there with the ideal gas law, PV equals nRT. Okay, so all we need to do are plug these variables in. The only one that's not noted there is R. R, remember, is the ideal gas constant, which is 0.0821 liters times atmospheres per mole Kelvin. So it's this wacky unit there, but that's what R was. Okay, so if we plug in there, the other thing we need to know before we start plugging things in, because R has these wacky units here, everything we plug into this formula has to match these 4 units. So the volume has to be in liters, the pressure has to be in ATM, which it is already, which is nice. Moles has to be in moles, which it is. If we had a mass, you'd have to convert that to moles first. And the temperature has to be in Kelvin. Okay, so keeping all that in mind, now we can plug into our formula. Alright, so if we plug in our numbers here, we've got 1.11 ATM. Volume is what we're solving for. Our mole value. R was the ideal gas constant, which we wrote up above, but we'll plug in here. If you don't want to put the units with everything, you don't have to. Just make sure they match up. And there's our temperature. So if we solve this, we just need to divide by the coefficient of our variable on both sides of our equation. So if you do all of that, whoops. If you do all of that, your volume should come out to be about 0.68. Remember, the unit is liters because that was the volume unit in the ideal gas constant. All right? So that was our last gas laws problem. If you need more practice, certainly go back and look at old quizzes, old homeworks, old notes. The next video will be on solutions, our last unit of the year.